Racket on top of Chez Scheme, two very well-known implementations.
All right, thanks everyone. To give you an idea of why we would rebuild Racket on Chez Scheme, this is a picture of the Racket version 6 main distribution. Like when you download it from the Racket webpage, this is line counts of the source code, and the different colors mean different parts of the implementation in different languages. So all of this blue here in the middle, that's good. That's all Racket code. The green code is also good. That's just the Racket dialect for writing documentation. But the red code down here, that is the motivation. In fact, we're going to zoom in on that. This red part, the core, that is the source code that goes into the Racket executable. If you just run Racket before it loads any libraries. And there are some various pieces here. There are the built-in operations. There's the garbage collector, which you might expect to be in C. But there's also like the bytecode compiler. C is not the right language for writing a bytecode compiler. And the macro expander itself, that's even worse. So there's a lot of C code here, and this is a problem. It has been a problem, and expected to continue to be a problem for maintaining the Racket implementation and improving it. 230,000 lines of C, certainly too much. And this is not the only way to do things. Of course, there are many examples of language implementations that are built a different way, such as Chez Scheme, where all of this purple code is Chez Scheme code to implement Chez Scheme. And this is where the compiler lives, as well as most of the built-in primitives. There's a small C kernel still, which is the garbage collector and bindings to file system and sockets and so on. This is the right way to do things, and this is the wrong way to do things. Right? And the fact that this is shorter, it's not just that Scheme code is more compact, but Chez Scheme is like sort of half as much functionality just out of the box from the executable, and that's the difference there. So we want to do something more like this, but when we started thinking about it, Chez Scheme was available in open source, so why imitate Chez Scheme? Why not just use Chez Scheme? And let's rebuild everything. And this is where we're going here, the picture on the right. So you can see a lot of the red was just replaced outright with Chez Scheme. A lot of the other red, the extra parts were converted into blue now, which means it's implemented in Racket, more of Racket implemented in Racket. This piece here that's still in red, that's kind of okay. Racket.io is like libuv. It's, again, the binding for the file system and sockets. The same kind of thing that's down here in the Chez Scheme kernel, just, again, a lot more of it. Right? So this, we believe, is going to be much more maintainable. And the question going in was, can we actually make this work? You might wonder why we picked Chez Scheme. There are many other schemes or other runtime systems out there. We could have gone to the JVM or .NET or something like that. But Chez Scheme, because, well, it's Scheme. You would think that taking one kind of scheme, Racket, and building it on another kind of scheme would be straightforward. And in fact, we get tons of stuff out of the box from Chez Scheme that we just need. All the number stuff is pretty much the same. It has a similar mode of operation to what we have experienced and built in Racket, which is on-the-fly compilation instead of a separate compile and then run phase stage. Continuations are pretty important in Racket, and Chez Scheme has one of the best implementations of continuations, including a path to get to the limited continuations. And the compiler is safe for space. We can predict what things are going to be live based on the original program, and that's preserved all the way through the compiler. So those are all our rationale. In fact, this picture on the left is kind of aspirational or approximate. Those pieces don't live in actual layers. But we did take a first step of moving the expander out first before we did the rest. And this is nice because it lets us make some more direct comparisons between the expander in C and the rest. Okay, so you might wonder where we are. Does it work? Well, of course, this slide presentation is running in Racket, and it's running on the Racket that's running on Chez Scheme. So, sure, it works well enough for me to give a talk. It works better than that, in fact. It passes the whole core test suite. For the test in the main distribution, there are hundreds of these. There's still about 50 failures that we haven't gotten around to. These are mostly things like error message checks. There are some other things that are more significant that we're still working our way through. We haven't yet applied it to all the packages in the Racket ecosystem, but we expect results similar to the main distribution because we have tried out a bunch of programs and things generally work. So we're on track, and in fact, it's a download option with the latest release. It's not the default yet, but we're hoping to get there. And the reason it's not the default is there are still some edges to clean up and even some performance considerations. This shows Chez Scheme is known to be fast on Scheme programs, and so traditional Scheme benchmarks the ones that are derived from the Lisp benchmarks and so on. The point of this picture is this RCS is Racket running on Chez scheme, so we haven't messed things up, is the message here. If you take those traditional benchmarks that ran fast, they still run pretty fast. We have had to do some things that do interfere a little bit, but not too much. And so on those traditional things, we're already getting better than the Racket implementation. The Shootout benchmarks, these are Racket programs, not scheme programs, so there's no purple bar, just the blue and the red, which is Racket on Chez scheme and regular Racket. And here we're getting pretty close. And the difference is, this is using all of that extra stuff that we put on top of Chez scheme, and they're much more representative of real Racket programs. So mostly we're seeing slight slowdowns, but it's slowdowns comparing something that's been developed over a couple of years over something that's been refined for a couple of decades. So we're pretty optimistic. Performance wasn't the main motivation here, but it does seem promising that we can get better performance at the end of this as well. Here's another kind of benchmark that's even more representative. This is, well, it's representative in some ways. This is building Racket, building the distribution from source. And since Racket involves a lot of macros, and macros are implemented in Racket, that runs a lot of Racket code. So here's the old implementation and the new implementation. You see we've gone from an hour and some to an hour and 20 minutes and some. So a difference of a third, but the outputs are actually significantly different here. Racket is compiling to bytecode, and then on the fly converts that to machine code. Whereas what we're getting when we build with Chez scheme is we're getting machine code up front. And it's doing register allocation and wonderful things like that that ultimately give you performance. So if we just look at the part of the compilation of the building that is actual compilation from fully expanded Racket code into bytecode or machine code, that accounts for 12 minutes at least of the difference, but this is not covering the macros themselves. So probably we're just paying more to get better compilation, which is a pretty good trade-off. Right? And generally this difference is very reasonable for build times. So that's some graphs about performance, and I'm not showing you a lot because I don't want it to be mainly about performance. The project is about making it more maintainable, and we have lots of anecdotal evidence here. Just from my opinion, we were able to re-implement these new layers more quickly, and they started to be reliable more quickly. In fact, the continuations part. Even in the early iterations of Racket on Chez scheme, it became kind of an oracle for what the old implementation should have done. So people would say, is this a bug? And I would say, looks like a bug. Oh yes, it runs correctly in the new version. Let's go try to fix the old one, which was a huge pain, which is what we don't want to do anymore. It's hard to put a number on these things, but I can give you one number at least. Right? This is the number of people who have been willing to modify the Racket macro expander. So this is when it was in C. 2 of us did it, and it already 6 people. And remember the C part, that was in the first 16 years, and the last 16 years of that implementation. And the 6 people in the new implementation is just in 2 years. Right? So we're really pretty sure it's going to be better to maintain. So speaking of the macro expander, this is the key part of the port to Chez scheme. The key first step really is being able to take macros and expand them and get them down to something that Chez scheme deals with. And the reason that's not obvious, after all, you're just expanding down to a core language, is the module system is tied up with that. So the module system used to be pretty core to the Racket implementation. And here I have a module that's a very dumb module. It creates a 0 macro that expands to an expression that always produces 0 the hard way by picking a random integer between 0 inclusive and 1 exclusive. And then here's a function that uses that. But I just do that so I have the 3 parts on the slide. So I've got some compile time code, which is the macro, some runtime code, which is the add 0 function, also useful, and some literal syntax. That hash quote is a bit of syntax that needs to bridge the 2 worlds, the compile time world and the runtime world, and preserve the bindings across the space. So how do we compile this down into basically the lambda calculus, right? That's what the 2 scheme systems can deal with. And it's almost lambda, it's called linklet, and that's because linklets, instead of taking values and returning values, they take variables that can be mutable and return variables that can be mutable. And this sort of just a slightly more complex layer gives the underlying compilers the information they need to do a good job, especially with cross-linklet, which corresponds to cross-module optimizations. And this little module generates 3 linklets at least. These linklets correspond to the different phases, and inside the linklets, they can just directly refer to primitives. So a lot of the game to porting Racket to a new implementation is to get all of those primitives set up. 1,400-ish of those primitives. Why are there so many? Well, there's plus and minus and fixed num plus, just lists and various core operations on lists that the library is built on. So again, that was why building on Chez scheme was easier than building on JavaScript, or say. We have to re-implement all of those primitives. Hopefully that kind of thing can happen for more runtime systems in the future. So a Racket module goes to these linklets, and then you can start to see how we build Racket on Chez itself when some of it's implemented in Racket. Right? The pile of modules that implement the expander turn into an even larger pile of linklets. We can take those linklets, though, and link them statically and then simplify the code. So we have a flattener that'll take a pile of linklets that need to be linked together and give you just one linklet. That just one linklet is not going to have imports, so it's basically a lambda, right? But it's a Racket lambda. So we need another little step called schemify, which takes Racket semantics into scheme semantics. Okay, we're down at the core level, so again, where do these things differ? Here's an example. So here I've got a function called h with 2 arguments. The arguments are a call to f and a call to g. Now in the scheme standard, you don't know whether g is going to be called first or f is going to be called first. That is, the arguments, the order of evaluation for arguments in a function call is not specified. A popular choice for some reason in language definitions. There's no reason to just arbitrarily break people's programs in the future, though. So Racket says evaluation is left to right, and so that means there's a difference in the semantics. And there's an obvious and easy way to fix this in this particular example. The schemify layer takes that application, and it just let binds f first, because let is specified to happen. The right-hand side is evaluated before the body in scheme. So schemify, that's one of its little jobs. And it adds the lets as sparingly as it can, just to avoid increasing pressure on the program that we pass to Chez scheme and what the compiler has to do there. But that's an example. Here is a more or less exhaustive list of all the things that we had to do to bridge Racket and scheme. So I talked about left to right evaluation. I'll talk about a couple more of them. The ones in blue and in purple, these are good. So the blue ones are the ones where we could, in our own adapter layer, adjust Chez scheme, adjust the code to work on Chez scheme. The purple ones are places where we did have to change Chez scheme, but they were changes that were attractive to the Chez scheme community, so they're already merged into the current version of Chez scheme. Okay. The ones in orange are not as good. These are places where we had to modify Chez scheme, and currently it lives on our branch to support Racket. And I'll talk about one of those in a minute, so you get a sense of what those are. The brown ones here are the same as orange, only we could get away without doing them, but if we've already got a fork, we might as well clean up those little details also. And we're getting pretty detailed here. We're talking about eq, which is pointer equality on flow num values, which is generally unspecified in lots of cases, but we're aiming for a very high level of compatibility between old Racket and new Racket. So we've looked at that level of detail. And there are some other things, the things that are in blackish or gray here, those are things we can do without. At least for now, it would be nice to get incremental garbage collection back or flow num unboxing for performance. But this is kind of, the paper dwells on this table and its details the most, because I think this is the unique part of the experience. You knew it was going to work, you just didn't know all the details, so these are all the details. I'll show you just a couple more of them. Racket has delimited continuations, which means that you can capture a continuation that doesn't capture the whole current one, but is delimited by a prompt. So that means we need to add call with continuation prompt and make call CC pay attention to it. It turns out that you can do this. You can implement this in Chez scheme by just using this internal $% current stack link. So $% means go get a primitive, one that you didn't mean to hand out to the rest of the world, but I know it's there anyway. Of course, Racket is very tied, Racket on Chez scheme is very tied to the Chez scheme implementation, so that's why we feel okay doing this kind of thing. And it's no coincidence that we can get delimited continuations, because the Chez scheme implementers have looked at them for many years before I did. On the other hand, continuation marks, sort of in the similar space, but Racket uses continuation marks as a way of reflecting on the current continuation. You can use that for dynamic binding or exceptions, stack traces, or kind of Java-like security models. That is, again, something you can emulate from the outside, but then it doesn't perform well enough. So we've had to sort of make some trade-offs between building things on the outside and getting the kind of performance we need. So this is one of those cases where we have patched Chez scheme with a kind of simplified notion of continuation marks called continuation attachments. And that's in our fork. It's not in the Chez scheme fork just because we haven't sold the Chez scheme community on this concept yet. But of course, I believe in this, so it's just a matter of time, maybe. But when you do that, and this sort of illustrates, when you add new things to the language, then it's not just adding a little bit to the library and Chez scheme in the compiler. It can affect other parts of the compiler. For example, the Chez scheme optimizer pass used to take let x be a call to some unknown function in x and just change that to call the unknown function. But if you do that, then you move something from non-tail position to tail position with respect to the let. And when you have continuation attachments in your language, that transformation is visible. So we had, again, to patch Chez scheme as part of that continuation, adjust the optimizer to do this. So the bad news is, I'm going to skip this one. It gets a little more, there's some more details about structures that can be applied, where this one was a schemify thing that we can transform the code in as few places as we need to make that work so we don't affect performance. What that means is that schemify ends up with some of the same analyses that an optimizer ends up with. So we're repeating some work in that sense, but we learn not to worry about that too much because it's all in Racket and scheme, so it's easy to maintain anyway. So we have these good things and these bad things. The overall point is that Chez scheme was a great starting point, and we're very comfortable modifying Chez scheme, which just reinforces our opinion that building things in scheme and Racket is going to work out better. You are not surprised by this conclusion, right? This is ICFP after all, but it's some extra little evidence that it does work out, and all the details are there. If you have a language, a functional language, and you're looking for a backend, I can highly recommend Chez scheme. It is the Lambda calculus, and it's got all the things you need that you don't get. You still don't get tail calls out of the JVM, right? Start with something that provides that to you. Thank you.
Thank you for that. We have a question from Slido. Are linklets compiled separately and linked using the system linker? And does the linker deal well with a large number of linklets?
So they are compiled separately, I would say, but not independently, in the sense that when you compile a linklet, the protocol with the expander cooperates. There's a protocol for the expander to cooperate so that the compiler can do cross-linklet optimization. So no, it's not using the system linker. It's using the linker that is a cooperation between the expander and the underlying system.
And do we have questions from the floor?
So,
yes.
In order to get the continuation marks working, you had to add a feature to Chez scheme. Is there a cost to that?
Well, there's, are you saying...
does it make other programs
Does it make
slower?
other programs? Right. No, this is another paper that I will be writing with Kenton sometime, but it has a very small cost. It was a new implementation technique, a better one compared to the old one. Yeah.
Another question from Slido. Are your patches to Chez scheme upstreamed, or do you need to use a custom version of Chez scheme to compile Racket?
Right now, you need to use a custom version. If you download the Racket source code, our copy of Chez scheme will be in there. Should be. We didn't package it quite right, but next time it'll be there. Or you use our GitHub repo. So, so far we've been able to maintain the patches and track the Chez scheme branch. And we'll see how it goes, works going forward.
Okay, we've got a question over there.
So when you do something like this, there's always a worry that you'll discover something that will be a real showstopper. That you rely on finalizers or weak pointers with a particular semantics or some debugger hook that was crucial to your debugger.
All of this stuff, yes.
So I wondered, so you ended up not coming across any, I mean, the showstopper might be of the form, you found some that you had to modify Chez scheme, you found nothing that really would require a big change. And you didn't know that in advance, so you made quite a big investment against that.
Yeah, the message said we're going to try this for a while and see if it works. And I think maybe it can work in a year. And after a year, of course, the message was, I still think maybe it can work. Give me one more year. So yeah, it was fortunate. But of course, had our goal been to use Chez scheme as is, we hit a number of showstoppers. Yeah. But Chez scheme was adaptable in the ways that we needed it to be.
That's kind of super important.
Yep.
Another question from Slido. You mentioned that you would recommend Chez scheme or recommend Scheme for implementing an FP language compiler. How would you weigh the benefits of Scheme versus something like ML?
Versus something like ML? I haven't tried to build on various ML existing backends already. I can only report on the Chez scheme experience. My guess is that, no, I don't think I can guess very well. I mean, there's the untyped versus typed trade-off in it, and you might get some flexibility from not having to encode things in a particular type system, but I don't know how much you would get. So I can merely say that Chez scheme is a good choice.
Other questions? Okay, let's thank the speaker.
Thank you.